In this video, we're starting section 3.2 on the graph of a function. Our goals are to go over how we sketch the graphs of a few common functions, and then we'll recognize when a graph has a hole and sketch the graphs of functions that do have holes. Okay, so in this video, I want to focus on the graphs of some common functions. Okay, so I'm going to zoom it out a little bit. So there are 6 functions I want us to look at. So there are 3 up here, and there are 3 down here. So for each of these functions, I want you to try to draw these. And I want to first have this be a warm-up and give you some time to try this. So pause the video for about 3 minutes and try to draw these. Some of these you might be more familiar with, some of these a bit less familiar with, but these are graphs that you probably all would have seen at some point before in algebra. So pause it in 4, 3, 2, 1, pause it, and try to graph these. All right, so hopefully you did that. Hopefully you paused it and tried to graph them. If not, go ahead and do that now. That's really valuable for you to assess kind of, where your skills lie in graphing. And then let's bring it back together. Okay, so absolute value of x, y equals absolute value of x. The graph of this looks like kind of a V shape. It's got this point at the origin, and then it's this upward facing V. So this point at the origin, 0, 0, it's called the vertex of the absolute value graph. Okay, all right, let's move on to the graph of y equals x squared. Let me draw the top 3, and then I'll come back and state all this information about them. Y equals x squared, this is maybe the one that we've seen the most out of all of these. This is our good old upward facing parabola with the vertex at the origin. So 0, 0, that is our vertex. Okay, what about y equals x cubed? So this graph kind of starts down here and then it snakes upwards. It kind of curves and flattens out at the origin. It goes through the origin. And then it kind of mirrors that snaking, but going upwards into that first quadrant. So this graph also goes through the origin 0, 0. But that point is not called a vertex for this graph. It is something called an inflection point. An inflection point. That's a term you'll see more in calculus, but essentially inflection point, is a point on the graph where the graph kind of changes how it's curving. It kind of changed from like curving downwards here to curving upwards there. And that's what an inflection point is. Okay. All right, so now for each of these graphs, these first 3, let's write down domain, range, and what type of symmetry they have. So for my absolute value graph, well, my domain, my x values, I can sort of see it by looking at the graph. Well, it's everything. Negative infinity to positive infinity, all the x values are in the domain. The range, my y values start at 0. This vertex point is the lowest y value on the graph. It's a bracket. I do attain that y value. And then they get bigger and bigger and bigger forever. So onwards to infinity. Okay, what type of symmetry does this graph have? It is about the y-axis. So it's the mirror image of itself across the y-axis. The part on the right is the mirror image of itself across on the left side of the y-axis. Okay, let's move on to y equals x squared. This domain is also negative infinity to positive infinity. All real numbers are in the domain. No x value gets skipped. My range also starts at 0 with a bracket. That's the lowest y value at the vertex. And then the y values get bigger and bigger and bigger forever. So it goes onwards to infinity. This graph is also symmetric about the y-axis. It's the mirror image of itself across the y-axis. Okay, for y equals x cubed, this one's a little different. Domain, again, it's all real numbers. Negative infinity to positive infinity. No x value gets skipped on the graph. I hit all the x values. For my range, my y values, well, they don't just start at the origin. I could also have negative y values going this way on the graph. So my range is just everything from negative infinity to positive infinity. Okay, what type of symmetry do we have this time? This time we have symmetry about, I'm going to switch to a different color. We got symmetry about the origin. And recall that what that means is if you take any point on the graph and you draw the mirror image of that point across the origin. So through the origin, draw a straight line to the origin, and then keep going same distance across. Well, you'll get another point on the graph. So this graph has symmetry about the origin. Okay, let's move on to the bottom three graphs. Okay, so D, I don't think this one is too bad either. I think the first four aren't too bad, and maybe E and F are a little bit trickier, but still not terrible. Square root, our square root graph. It's kind of starts at the origin like this, and then it curves upwards like this. So this also goes through 0, 0. And on the square root graph, I'm going to call this point the initial point. So there's a graph where square root functions like this sort of begin, and I'm going to call that the initial point. What about y equals 1 over x? Y equals 1 over x, this graph has two pieces. There's one piece up here in the first quadrant, and there's a mirroring piece over here in the third quadrant. So the shape of this graph is something called a hyperbola. For this graph, I'm going to label a couple points. So if x is 1, and I plug in 1 for x, the y value is also 1. So it goes through the point 1, 1. And then if x is negative 1, and I plug a negative 1 into here, well, the y value is also a negative 1. So labeling these, it goes through 1, 1, and then negative 1, negative 1. I don't really have any special names for these 2 points, but those are just 2 common points that y equals 1 over x goes through. Okay, my domain, well, there's only one x value that gets skipped, and that's right here when x is 0. So my domain is negative infinity to 0, parentheses, I don't ever achieve x equals 0, union, parentheses, 0 to infinity. I can also see zeros get skipped from the formula, because in the formula, if I were to plug in 0 for the x, the denominator is 0, and that's not allowed. That's the only bad x value that I'm not allowed to plug in. Okay, what about my range, my y values? Well, the smallest y value is way, way, way down here, and they get smaller and smaller and smaller forever, so they start at negative infinity, and then they get bigger and bigger and bigger, and they get really, really, really close to where y is 0 as I get closer to the x-axis, but they never reach y equals 0. So y equals 0 gets skipped, and then I jump ahead to positive y values over here, and then they get bigger and bigger and bigger forever. So union, parentheses 0, onwards to infinity. So the only y value that gets skipped is y equals 0. Okay, so does this graph have symmetry? Yes, this graph has symmetry about the origin. It's got some symmetry about the origin. Alrighty. And this graph also has what are called asymptotes. It's got a vertical asymptote. Let me go ahead and draw it in. The vertical asymptote is right here on the y-axis. So I can write the equation of that line down. The equation is x equals 0. Because every point on this vertical line, it's got the same x coordinate. X equals 0 for every point on that vertical line. That's the equation. Okay. Typically, when an asymptote is on an axis, we don't draw it in. I tried to draw it in just to emphasize that it's there. But usually, if it's on the axis, we don't draw it in. But if it's off an axis, we definitely draw it in. This graph also has a horizontal asymptote, and that is at the x-axis. Okay, so the equation of that line, well, every single point on this horizontal line, it's got the same y value, and it's y equals 0. So that's the equation of that horizontal asymptote. Again, it's on the axis, so I don't really need to draw it in, but I just wanted to really emphasize the fact that it's there. Okay, so asymptotes are curves that the graph gets really, really close to as I go very far out. So either far out to the right or far out to the left, or if I go really far up like this, or if I go really far down like that. Okay, I realize I skipped domain, range, and symmetry for my square root graph, so let's go ahead and write those in. My x values start at 0, it's included, and then onwards to infinity. My range, the y values, also start at 0. That's the smallest one. And then they get bigger and bigger and bigger, so on to infinity. This graph has no symmetry, though. It's not symmetric about the y-axis, otherwise there would have been a mirror image thing over here, but there isn't. It's not symmetric about the x-axis, otherwise there would have been something like that, and that's not even part of the graph. It's not symmetric about the origin, otherwise there would have been a mirror image type thing here, but that's not there either. Okay, one final function to go. This one I think is maybe the hardest out of the 6 to remember. So let's talk about how I could figure out what this graph is. Maybe if I couldn't remember it or didn't know it. So maybe I don't like the fact that there's a square root here and something kind of more complicated inside. So maybe I'll try to get rid of the square root by squaring both sides. So that gives me y squared equals 1 minus x squared. Square both sides. And then let's get all the variables on one side. So if I move x squared over, I will get positive x squared plus y squared equals 1. And this hopefully looks a little bit more familiar. We saw this in chapter 2. This is the graph of a circle. This is the graph of a circle here. So, well, does that mean the graph of my original function is a circle? Well, almost. So not quite. So if I think about y equals square root of 1 minus x squared, there's something that I want to notice about this that indicates that it's not going to be the full circle. It's just going to be part of it. And it's the fact that no matter what I plug in for the x, this whole thing, I have this big old square root here. So no matter what gets plugged in, when I square root my number, this whatever I get out of the square root can never be negative. So that means y is never going to be negative. So there's no way I should ever end up with like negative y values, which would happen on the bottom half of my circle. So because of that, this formula just refers to the top half. Just refers to the top half of the circle. I'm going to draw that in. So the top half, or in other words, I could call that my semicircle. So the radius of this circle is 1, because I square root that number. Okay, so this endpoint here is 1, 0. Over here is negative 1, 0. And then up top would be 0, 1. We call those special points the poles of the semicircle. This is kind of like the North Pole. And I can also think of there being poles on the sides of the circle. Okay, of the semicircle. We call those the poles. Okay. This might still be a little bit, unsatisfying. How come, all we did was just kind of do the same thing to both sides, but how come when we did that, the graph is different? Like this graph here was a circle, but the graph of what I started with is just the top half. Like how come they aren't exactly the same? Well, so that has to do with the fact that these steps that I did to simplify it, they aren't perfectly equivalent and perfectly reversible. Like in fact, if I were to take this equation and try to go back in this direction by square rooting both sides, well, if I were to square root both sides and get a square root on this term, well, I would have to put a plus or minus in front of it when I square root both sides. So I'm going to consider, well, if there was a minus in front of it, what would that then look like? Well, if the square root outputs non-negative values, having a negative in front of it is now going to make it never be positive. So that's going to correspond to the bottom half of the circle. Okay, so it is true that x squared plus y squared equals 1 is the full circle. And if I were to isolate y to bring it back to this form, well, a plus or minus end up showing up. And each of those corresponds to just part of the circle. And that's another way I could see, wait, that is more believable that it is just the semicircle. Okay, let's get my domain. My x value started at -1, bracket to +1. My range, my y value started at 0 with a bracket up until 1. That's that highest point. Brackets at all of those because we do reach each of those points. And symmetry is about the y-axis. This graph is the mirror image of itself about the y-axis. Okay, so these, just to recap, these are the 6 sort of basic graphs or common graphs, I would say, that we definitely need to know for our class.